In this video, we will talk about the basic properties of logarithms, which goes along with the first Newton assignment assigned for section 4.5. So the first learning objective that you might be assessed on in this assignment is understanding the basic properties of logarithms, right? So really what these are testing are that we recognize that logarithms are the inverses of exponentials, right? So if we look right here, we can see that we have the logarithm, the logarithm with base 13, and we also have the exponential with base 13, right? So if we have the logarithm and the exponential with the same base, these are inverses of one another. Right? And so what that means is that essentially these are going to cancel out and give us just that original input back, right? So this will cancel out and just leave us with 9, right? And what the two, this is one of the inverse properties, right? This is the one where we are composing the exponential, and then we're plugging in the logarithm. Right? We can also do this with the other order, right? We can take the logarithm and plug in the exponential, right? But as we know from the definition of inverses, right, when we compose those two inverses, they have to simplify to just the original input. Okay, so in this next question, it's still testing the inverse properties of logarithms, right? It's just we have to select all of the statements that use inverse properties, right? So like we just saw on the last slide, what we're really looking for is anything where we have the log and the exponential with the same base, and they are canceling out, right? So remember, the logarithm is base e, right? Sorry, the natural logarithm is base e, but if we look at what's inside here, that's a base of 4. So those two are certainly not inverses. Right, in this next one, we have the logarithm with base e and the exponential with base e, right? So those are going to cancel out and just leave us with 4. So that one is an inverse property. Again, here, the e is not the base in this next one, it's the exponent, so that wouldn't be an inverse property. And in this last one, we have the exponential with base e. And we're plugging into that the logarithm of the base e, right? So we are composing inverses there. So these should cancel and just leave us with the input of 4, right? So that one is an inverse property. Okay, so this first learning objective was just testing those inverse properties. And now we have a few other properties of logarithms that we could be tested on. And so this one says we are looking at the product rule for logarithms, right? So remember that what the product rule for logarithms tells us is that if we have the product inside of a logarithm, right, we can break that up and write it as a sum of two separate logarithms. Right? And remember, we can always interpret the product rule going the other way as well, right? So saying that if we do have a sum of two separate logarithms, right, as long as they have the same base, we can combine those into a single log by multiplying what's inside. Right? So in this case, we're going to be using the first one, right? So we're going to be taking this log where we have a product on the inside, right? 5 times 3 minus 2x, and splitting that into two separate logs, right? So we're going to take that and split that up as the log base 2 of 5 plus the log base 2 of 3 plus 7x. Okay, and you can still see there is actually a term here that's a product still, the 7x, but since that 7 is not something that we can factor out of both of these terms, it's not something that we can simplify further, and so this would be our final answer for this question. Okay, so if we look at one other example of how we might be asked to use this product rule for logarithms, right? Remember when we wrote down our product rule, I said there were two ways we can interpret it, right? We can either start with a product on the inside and split it into two logs like we did on the last question, or we could be given a sum of two logs and being asked to combine it into a single log. And so that's what we would be doing here, right? So I'm going to take this sum of two separate logs, right? And since they're being added, the product rule says that I can just multiply the inputs together, right? So 7x times 2y. And so that would give us the log base 4 of 14xy if you were to multiply that out, right? So that's what we would type in as our answer here. Okay, and now the quotient rule for logarithms basically is a parallel of the product rule, right? So we said that products were related to a sum of two separate logs, right? So for a quotient, we know that the quotient rule says that if we have a quotient, it can be split into the difference of two logs, right? So again, if we start with the log of a quotient, we can split that up into the log of the first minus the log of what was in the bottom, right? Or sometimes we'll be asked to work the other way and take a quotient of two separate logs and turn that into a single log of their quotient. Right? I don't know what happened to my or there. Let's fix that. Right, so those are kind of our two versions of the quotient rule. And in this case, again, we'll be using the first one because we're starting with a single log of 8 divided by 5. Right, and so all this says is that we can split this up into the log base 2 of 8 minus the log base 2 of 5. Right? And so technically you could simplify this a little bit further because the log base 2 of 8, right, that's just asking us what power would we have to raise 2 to get 8, right? So this whole thing could just simplify to 3, but this was just asking us to apply the quotient rule, not necessarily to simplify it completely. So this answer would be enough for this question here. Okay, and again, you might see questions like this where we're starting with kind of the first version of this quotient rule that I wrote, right? We're a single log of a quotient and we're splitting it into two pieces. Or we could see something like this where we're starting with a difference of two separate pieces and being asked to combine that into a single logarithm, right? So again, it's the same quotient rule, but now we're thinking of this version of it. Right? And so if we were to combine these two, it becomes a quotient. So we have 10x divided by 2, right? And that input on the inside could just be simplified then to 5x. Okay, and so the last property that you'll see in this assignment is the power rule for logarithms. And remember what the power rule told us is just that whenever we have the logarithm and we have something inside that's being raised to a power, right? So x to the p, that power can be brought out front and we can turn this into multiplication. Right, and remember, all of these rules can always be interpreted both ways. So we could also start with a number out front and say that what this tells us we can do is bring that thing inside as a power. Okay, so for this particular problem, we are looking at this first version, right, because we're starting with the power on the inside. And so what this power rule says is we could just take that 3 and bring it out front as a coefficient, right? And so the answer here that matches that would be this one right here, 3 times the log of k.